and why do you want to use cloud for robotics? So, so to give you a sense, Jeff Kuffner coined the term in 2010 of cloud robotics, and it's generally trying to solve a problem where local robots do not have sufficient or a lot of computational power. On the other hand, you have this increasing, demand and equipped with cloud computing that can provide almost unlimited computational power to this robot. So the solution to this is to give the robot internet. And this has a lot of benefit, including you can actually leverage all the big data you have in the cloud now, and then you can perform statistical learnings. People can share codes and then share applications, designs with each other, and on top of that, robots themselves can share data. An analogy I have for this is, remember when I discovered internet as a kid, right? And then we want to do the same thing for the robot. Have them to have more knowledge and then equip them with more, more capabilities using the cloud. Now, the caveat is there are network latencies and variabilities, and then we are working in a heterogeneous network environment, and a lot of robots rely on reliable control. Unlike us, we can just sort of figure it out. And on top of that, privacy and security would be a concern. Imagine if in the future you have a robot nanny where you put it in people's home, you would not want the robot to harm your kid or family in any way. So today I'm generally going to talk about two models of cloud robotics, particularly in the realm of hand manipulation and then grasping. And the first model I will talk about is robot and automation as a service. This is very similar to software as a service, this type of concept before. And the second model I'm proposing, and I'm giving you some demonstrations of how this could work, is leveraging the hybrid between the cloud and the edge device, and use the edge device as a cloud robot accessing point as well as a robot controller to control robot. And specifically, I'm going to talk about human-robot interaction using this particular system. So, so this is a previous work I've done in Ken Goldberg's lab. So as a biologist or a biomedical engineer, the first thing Ken asked me to do is figure out how to do multiple pick and place. It's like the simplest task in robotics, but connecting Dex-net, right? He has this great system called Dex-net that can provide a lot of the best robust grasping recommendations given a 3D CAD model. And he has this large data set, tens of thousands of models were stored on a server, and Jeff Mahler actually created this system where you can use reinforcement learning, multi-arm bandit combined with Monte Carlo sampling in order to figure out the best robust grasping there is for any particular object. But the problem is, each one of this object, this whole process would take maybe 1 to 2 minutes on a standard computer, and you have thousands of objects, and what would you do? You can never actually really do this in real time, right? So one of the ideas we came up with is to cache all the pre-processed grasping recommendations in the cloud using its large storage, and then build the cloud as a recommendation system. And having the local robot query this, pre-cached grasping informations, and for the robot to decide what to do locally. And the demonstration, and this is an example of what the output of the Dex-net is. Basically, each one of the vectors you see on the object represents the grasping, a parallel gripper's grasping contact point with the object itself. And the color is actually encoding, the green color is actually encoding the highest, the more robust grasping recommendation you will get from this system. As you can see, initially this is the recommendations you got. You got over 200 recommendations from the system, all run to a certain matrix, such as Ferrari, Kenny, and others, in terms of measuring the robustness. And what we did in this system is we filtered out the top 15 out of 200 grasping recommendations that that indicate all of these objects, all of these grasping positions are very robust. And then because the particular application we are looking at is concentrated on a top-down grasping position, so we would want this grasping vectors to be as parallel to the table as possible. So we actually impose a heuristic on this, selecting the most parallel grasping vector out of this 15 recommendations. And then this is the result on the right side. So as you know, we have 6 different chess pieces, and as a note, you probably noticed by now, these are not standard chess pieces. These are non-standard wizard type of chess pieces. And these are the final grasping recommendations we got from Dex-net, given the constraint we put on this system. So to compare the benefit of using Dex-net to a typical hard-coded X and Y grasping that is along the x-axis and y-axis, you can see there's some poor performances on the queen and then on the bishops in the hard-coded axis. But in the end, if you were using Dex-net and the heuristic we imposed on, then we got over 98% of success rate of all these objects. But we think we can do better. So it's 98%, but when you're playing chess, if you miss by 1, so it's multiple consecutive movements, right? If you miss it by 1, the entire game fails, right? So we want to get 100%, almost 100%. On top of that, we want to remove the heuristics we imposed on the system. So one way we think of doing is actually to perform the actual experiments to complement the imperfections in the simulation. So as you can imagine, all these experiments can be very expensive to perform, right? You have to have an operator in front of the robot and all that. And then on top of that, robots are expensive. And then it's very costly to perform this kind of experiment. So this comes as an idea of building a collective learning system where you can record all these experiments with many, many robots. In concept, this is just a proof of concept because the ABB Yumi arm has 2 independent arms. We can perform the experiment twice as fast. But imagining you have a whole factory of this robot, and you can actually just perform this kind of empirical experiments in a very short time in parallel, so that you can speed up the data collection process as well as the ranking process of this data collection system. This is all come from the benefit of connecting all the robots to a centralized cloud robotic platform. So what we demonstrated here is by actually performing the empirical experiments, so in the case of this bishop or the dragon piece we can actually filter out a lot of grasping positions that is seemingly a good idea, because if you look at this grasping examples, the top 5, except for the number 1, the top 5 are actually very similar. And if you just look at them visually, you would think almost all of them could be a good idea, maybe except for the number 1, right? So, but when you are actually performing the experiment, you realize, number 2 and number 4 are not so perfect. They are grasping, 2 and 4 are grasping on, a sliding surface of this piece, and it ended up not working so well. So this is just an example of combining an empirical experiment with a simulation. You can create a more powerful system. And with a collective learning module, you can actually perform the empirical experiment much better. And this is the end result, and you have already seen it. This is 2x fast, and then this. So we can actually play any chess game on this. Parsed with, the PGM format. So we want to see how far we can take this idea, right? So this idea of using cloud robotics and have a recommendation system in the cloud. So we decided to partner with this company called CloudMind, who has a state-of-art cloud robotics system platform called HARI. HARI stands for Human Augmented Robot Intelligence. I'll explain what it means later. But under this context, we specifically are leveraging their network capabilities. They have a very good, reliable, fast network that is, between across the Pacific, as well as potentially can deploy around the globe. So, we actually have to benchmark, how good their network is, and why do we actually have to use their networks or their products over other products. And then this is the demonstration we have done. So we actually deployed Dex-net in Oregon on the EC2. So this is all on the West Coast. And then we have our robot reside in the Santa Clara office in the South Bay. And this is the first scenario. And the second scenario is we deployed Dex-net in China and have the same setup here. But we are using the normal network, the typical network you would use. And then the third scenario is we are replacing, the normal network with the cross-border network you would normally use, and this cross-border network is part of the HARI platform. And the result we get is this. So if you were to put a server locally, there's very minimum delay, all variances. And if you are querying from just the West Coast, you can support maybe up to 30 hertz in the U.S. This is the delay and the variance we got. So within the U.S., the network is very good, right? So, but if you actually want to provide services across the globe with a single server, then that's a different story. If you were to use the normal net, then the delay is 300 or so milliseconds. That only support up to 3 hertz. It's probably sufficient for the chess demo, but may not be sufficient for other things. But look at this variance. It's about 54 millisecond variances, and you wouldn't have that kind of trouble. Yes, the latency is lower with a cross-border net, but look at the variance. The variance is actually very low. So that means you can provide reliable 5 hertz control signal across the Pacific. This is just, of course, I'm not saying that every single robot should be should be controlled from the other end of the world, but in order to provide a global services, this kind of reliability is important. On top of that, this cross-border network has also guaranteed there are certain security measures that put into this that tie to the performance of this network, but also guarantee the privacy of the user. So just we kind of look at why this is, why the variances, the differences in variance between the normal network and the cross-border network, and you can see that on the normal network, because of maybe multiple routes and then all the routing issues, there's a lot of dropped packages in the networks that forces the network to reroute the package that causes most of the delay in the network. But if you look at the cross-border networks, they have almost minimum no package drop across this long distance. So a byproduct of cloud robotics having services on the cloud is teleoperation. So here we are actually demonstrating, we have CloudMind's people deploy their user interface in Beijing and have Dex-net in Beijing, but we actually have the robot in the US. And we are actually perform real-time teleoperations. You can see the robot, kind of what you would see on a FaceTime or something. But you can also control the robot with minimum latency, things like that. So the advantage of robot and automation as a service is you have a very simple robot. You can have a very simple robotic interface to program on. You can actually accommodate many different kind of developers, very heterogeneous like computing systems. And then you can learn knowledge from large-scale data set. You can enable data sharing across different robots. And if you have a reliable network and secure network for robots, then everything pieces together. And then just to have fun, we have programmed all these other little demos to show we can do visual feedback, visual correction for this robot. With this system, we can do immersive VR and AR control, and then we can also use a mobile phone to control the robot. And all of this can be deployed from the other side of the world to here, right? I can control, like this, for example, this VR example, this is purely, the communication is purely network. That means we can deploy this Windows system on the other side of the world and have this robot still work in the US, and Dex-net is also a Linux system. So it's all sit on the same network standard that accommodate different systems. Therefore, we kind of pitch this idea of the value of cloud robotic services outweigh the communication costs. And right now, it seems like it may be the case, but look at this. 5G is coming, right? So the network is only going to become faster and faster. By faster, I mean more bandwidth of a specific application. For example, with 3G, when you download a movie, it takes 26 hours. 4G takes 6 minutes. But with 5G, it's a standard they're proposing, it's only 4 seconds. Why would a human need this kind of speed, right? Like, we actually use our phone to look at video streamings and know that satisfies almost every day of our, the need for the internet. Why do we actually need this? So the proposed idea, proposed by Bill Huang, like the CEO of the CloudMinds, is, the 5G is for robots. It's for all the sensors, all the visual sensors, perception sensors that's gonna integrate, talk to each other, and then they're gonna use this bandwidth, to talk to the cloud and each other. So in the future, this statement may very well be true. The value of cloud robotic services outweigh communication costs. But there's one problem, which I think I lost my slides. Let me just state the problem, right? So what is the problem? The problem is you can never beat latency because latency is bound by the speed of light. So you can increase however the bandwidth you want on this network, but you really can't beat the speed of light on latency. So how do we deal with that? We actually have to take care a little bit in terms of
change your location usually.
I'm sorry?
You have to change your location usually.
Right, exactly. So you can actually deploy potentially a cloud that is a lot closer to your robot. But think about this. What if there's like a massive outage in the data center, right? So it's not just about latency. It's about what kind of autonomy need to reside within the robot that guarantees that when the cloud is gone or the network is gone, the robot can still kind of sustain its normal functionalities and know that. So this is why we want to propose like a hybrid approach. But before we go there, why do we want to do this, right? Why do we actually want to have this hybrid approach? The reason is we want to have our robot work in a service type of environment now and in the future. So what is a service robotics? The service robots offers semi or fully autonomously to perform services useful to the well-being of human equipment, excluding manufacturing operations. I think this last part is probably kind of partially biased by this institute. But the point is, a service robot is supposed to perform human-assisted tasks. They are not industrial robots where all the environments are predefined and they care about accuracy. The service robot actually need to accommodate very complicated environment very fast, and then have the ability to perceive them and have the ability to respond to them, particularly under a very dynamic environment. So to give you an example, right? So this is maybe like 2 years ago. This is in Germany, and then they're proud of their beers. Therefore, they have a robot that can pour the customer a beer. Look at this part. So if you look at this, like all the bottles of beers are all lined up, right? And then even the openers lined up, right? And then they go to a very specific locations to pour this beer, right? So I mean, you guys are probably guess like there's almost no visual perception in this one. Because think about it, visual perception is already pretty hard to look like transparent glasses, bottles. If they had visual perception, why would they actually have to line up the beer and then put all this environment very organized way? But also notice this very last part. It holds the beer to the exact same location, so that the bartender can take the cup and then give it to the customer. It cannot actually directly give it to different customers, right? And therefore, so what's the takeaway of this demo? Of using a traditional industrial, way to program a service robot. So, more general perception is important. More generic visual and force feedback control is important to actually respond to this dynamic and more general perception. And on top of that, human-robot interaction can be more natural in this case. Well, maybe cloud can help in some perspective. So, we go back to this hardware platform built by CloudMinds. So their idea is to build a cloud-based system that can host deep learning system on it, so that the local robot does not have to spend a lot of computational power locally to waste power, energy, or equipment and stuff. And on top of that, they also want to use human intelligence to inspect this whole process. So their idea is that in the near future, we are still very far away to have a service robot that can accommodate very generic human-robot interaction environment. So what's the mid ground here? So maybe we can use AI to assist what the human can do, and then maybe teleoperate the robot to a degree with like certain autonomy. But on top of that, when the robot cannot perform certain tasks, you have the human to jump in and then perform the task or demonstrate that task to the robot. So over time, this system can potentially learn more and more human-like actions for human-robot interaction, human assistance, and all that. So the system are composed of two parts. One is the cloud part, which is the brain of this whole system. And the other side is actually the edge device side, right? So you use a phone to access their private LTE, and then also use the phone to control all these end devices. So they see this phone device as the spine and the nerves of your body. And then that connects the brain, that is a higher level function, to the muscles, which is the robotic arms. Well, here's the missing slide I'm looking for. It's in the wrong place. But but the point is this. So if you because we want to perform more dynamic controls, we want to push the dynamic control to the edge. Right? So this summarizes what I just said about cloud services, which is less than 1 hertz. You can actually have a lot of connective learnings. Right? You can have transfer learnings from the cloud. You can transfer your deep learning models to here, to the local robot, and that's less than 1 hertz. right? But then you have tasks that is like, for example, catching a baseball or throwing a baseball, that you actually need faster than 100 hertz at least, kind of perception maybe, control maybe, and all that. But all those two things only covers, individually only covers a small fraction of the application area. But a hybrid that can actually, a hybrid of the two can actually support most robotic applications that is between 1 to 50 hertz control signal. So the general rule of using this hybrid system is that if you have need of increase in dynamics controls, right? But you don't actually need all these high-level reasonings, or maybe very long-term goals, then go to the edge. But if you actually need very thorough, complicated reasonings, maybe perceptions, then you want to actually move it over to the cloud. And then having this hybrid system can potentially compensate for both. And this is, kind of like a rough sketch of, what I think it should happen, with Hari, given the framework. So you have human command that goes through the Hari cloud and then can provide other recommendations, like happens in the Dex-net, as a service you provide it to the robot, or you can provide high-level high-level controls based on perception. And you would have a single local robot RCU to control individual robot, and then close up this control feedback loop with all the perception sensors, either in the robot or on the edge device. And I want to test some of this idea in the human-robot interaction. The reason interaction wrong, the reason is, the human-robot interaction actually solved the big problems in a service robot, which is interacting directly with human. On top of that, it has many potential dynamic tasks we have to compensate while working with human. And a lot of our perceptions, for example, mass RCNN, right? Like perceptions are kind of out there already. And then if we can actually deploy those very good visual perceptions in the cloud, but using a dynamic kind of algorithms to respond to the visual perception on the local level, then we have a very good system. So what is human-robot interaction? So it's the understanding, design, and evaluation of systems used by humans. And in this survey paper by Gottridge and Michael in 2007, they classify, they identify two kinds of human-robot interactions. One is remote interaction, which is teleoperation. We kind of already see that already. And there's proximate interaction, which can be dynamical interactions, and then it should be it can be communication, which is I'm making all my nonverbal gestures, and then the human would understand what I'm doing. Or the robot, when the human in front of robot acting all the same kind of gesture, the robot would understand what the human is doing. And there's the ultimate physical interaction between the robot and human, and then we're gonna see all three of them in this talk. Let me speed up a little bit. So this is a teleoperation system that cannot deploy in long range. And the reason is, we are using Kinect, and then this is performing general human gestures. But in order to send in the sample point of the trajectory that you're doing, the human gesture can be very unpredictable. Then, with high latencies, this may be able to you may be able to do this with a single server, with a single robot, but you definitely cannot perform achieve scalability, meaning a single server may be serving 10 or 20 robots at a time. So we kind of want to shrink our constraint a little bit. Maybe we shouldn't go for the full gesture following imitation scenario first. Maybe we should go for a subset of gesture following. So we identify, maybe this is a good project. We want to perform semaphore following human gestures. And the reason being they are all 2D gestures. I don't need 3D cameras, and they're on a cell phone, right? And then they don't have 3D camera yet. And then you can actually, they have like a very compact well-defined alphabetical representations that is good for communication, and it is also useful for long-range communication in general in the real life. So there's two parts of this. So the big thing we did for this project is we moved the perception, we moved the object, the gesture recognition into the cloud. We are actually leveraging CMU's open pose that can infer skeletons using a deep neural network, and then to detect pose. And we basically defined, what's the angle between the torso and your end effector, and then how to, what's the definition of, and then use the definition of semaphore to infer what they are. And then there's demonstration. We are actually doing this in the cloud, but having the user looking at the screen perform semaphore. As you can see, this is pretty decent. This is real time, maybe like 5 to 6 frames per second, but it's good enough for this application. And then I'll show you why it is good enough. And then in order to actually solve the problem I told you about the general gesture following, what we decided to do is we pre-generate all the trajectories between all kind of semaphores, 26, between all kind of semaphores, and we store it on the end device. And then through the store on the edge device. And then when the cloud decided, okay, I want to follow A, then the cloud would send the A letter to the local robot, and the local robot actually would decide which trajectory to follow from our current state and move it into the A position. And this is the overall architecture. You can see camera, video stream, recognition, and semaphore commands, and then send it back to robot arm controller, which is a smart pad on the robot. And one thing you'll probably notice is we are actually using this network very efficiently. We are actually using compressed video streams through this network for video streaming, and then sending back. We are only sending back letters. We are not sending back the full trajectories back to the robot to command the robot. And that's the end system. Let me see if I can show you. And this is no speed up. And the reason you're seeing that little bit of delay before is not because of network. It's actually because we want to guarantee that the recognition is solid. So we actually take more time points to estimate the state of the human gesture before the robot decided to move in one way or the other. And we actually deploy this robot and this entire system in Japan while hosting it the server in US, and it works pretty well. And we kind of made some analysis on how latency played out in this system. We kind of realized that the human user eventually can learn how to hide latency by themselves. The way it works is through recognition. So this is the video streaming latency. This is a human gesture demonstration in Japan, and then this is the video latency. And then see, this is where the command was sent, and then this is the latency of a command. And both of this latency is here. This is half a second, but the actual motion of moving semaphore from one position to another is on average 3 seconds. So we didn't intend it to hide this latency, but the user somehow figured out when the robot is moving the arm, they can actually perform the next semaphore. And then by the time the robot finished that motion, then the system already recognized and maybe even send a command for the next semaphore. So we are adaptive to this human-robot interaction system as well as the robot system. what comes next? So I just find out there's this generic 3D gesture system that's only based on 2D cameras, and then I want to try this to see if we can actually perform generic 3D imitation on a large scale using cloud robotics. This is near future work. So it's not done yet. I have 10 more minutes, and then I'm going to show you a little bit more stuff. So while we were at this, while we were performing all this general gesture following stuff, we were like, oh, can we actually guide this packet robot made by SoftBank to pick up object? If we can actually even do this, right, with very, preliminary hand with no force sensing, that would be cool. And there's like a big market you can go into and solve this robot. But what you end up seeing is you can't really. There's multiple reasons, right? So basically, so the robot or maybe the operator got so frustrated that it just slammed the hand across the table, get all the objects. It cannot actually even pick up a single object. So what does this mean? It means like we need. There's a need to locate object visually, right? And then the problem is, look at the pattern. So these are their cameras. They're on like an unstable platform. This head is moving all the time. You cannot perform, camera registration every single time when you decided, oh, this head want to move left, and then I have to put like a chessboard inside and to register this camera again. To this whole robot thing. And then that's the traditional, industrial robotics thinking is I have to register the camera with the entire word frame and different frames so that I can perform very well. So what we need is visual servoing, meaning by measuring the relative distance of the object you want to manipulate and your end effector. And maybe you can generate passes, dynamic passes, that can eventually achieve what you want to do without registering the camera. And then on top of that, the operator cannot feel when the robot is touching the object in the lab. And that's a hard problem because that tied directly to the hardware you're using. So this hand doesn't have force feedback. And it doesn't matter if we have a haptic systems or not for the teleoperation system. It cannot actually provide any force feedback when the robot is in contact with the object. So how to do a perfect dynamic object pickup? We can do a perfect dynamic object pickup yet with every single object, but we can maybe potentially pick up a box. So what we really want to try is we want to try visual servoing using this dynamic self-balancing robot. So the self-balancing robot itself, the system module itself, is a dynamic task already. You cannot directly control this robot from the cloud to keep this robot upright. And by the way, this is the Igor robot made by Happy Robotics. It's a close partner of Cloud9's. And then they built this robot for us, and then we actually are working with them to integrate the phone and the Harvey platform onto this robot. So we come back to this Harvey platform again. So perceptions, commands, maybe trajectory generations, which is all less than 30 hertz, can probably put it onto the cloud because you need more sophisticated object recognitions and trajectory generations to perform high-level intelligence. But the motion control that is greater than 200 hertz need to stay at the edge device. And these are the breakdown of where what we want to put in the cloud and what we want to put in the edge. And to start, we actually want to control this dynamic arm with the same concept as the semaphore system, where you have a pre-generated trajectory that is stored or can calculate it onboard, but were commanded from from another system. So we thought, okay, making Igor dance, like disco motion, maybe is a good enough demo to do this. So this is a way to show, we can actually perform dynamic trajectory followings with command coming from the cloud. And then this now, we are only using QR code, but this recognition happens in the cloud. And we are actually using this recognition system to guide the robot through visual servering so that this robot can actually go and pick this object up. Nothing's registered. Here's the phone that has a 2D camera on it. We are actually just using this 2D camera and to pick up this object. And this is a stationary object at the moment. So the robot approached the object and then decided, lower their arms and then the torso to pick up this object. All of these commands were based on the relative measurements, the relative motion distance measurements between this box and the phone. And we bumped the phone many times, right? Like this is not like a very good, shelf or something. We bumped it many times, and then we go back, and then we just put the phone back on again. We don't have to do anything. This whole demo would work as soon as we put it up. And I wish I have a better video for this, but this is kind of a demonstration where this robot can pick it up from a human. So the reason I'm saying this is not a very good video, and I wish I have taken a better video, is that right now you kind of see this object being fairly stable, held by human, but in real life we actually tested out. We can actually use this box as a cue, and then we can move the box however we want. As long as this robot can see the QR code, it can actually come to you. It would follow you, kind of like a robot stalker. And it means that it can follow you and then come in, and as long as the height of the box is reachable by the robot, you can pick it up through the same system. And this is also demonstrating, there's some hybrid control. After this box is picked up by the robot, then because we haven't programmed a dynamic robot-human handover yet, then the operator in the cloud can actually complement this autonomous system to give this robot to the human. As you notice, right, like it's not a very intuitive way to control this robot and then give it over to the to another person. This is it's actually very hard for the teleoperator to do. So the initial pickup was actually very good. The pass and all that is all smooth and autonomous. So conclusion, we programmed a proof of concept cloud and edge-based hybrid system. It's important for large-scale service robot deployment. It can provide a dynamic robot pickup object from human, and we also leverage the hardware platform and visual servering in all this cloud-based robotic work. So I would like to thank my advisor Ken Goldberg, and then advisor Professor Samoyan Sujordi. Jeff Mahler and Matt Mao have put have given me a lot of help to start the Dex-net project. And the undergrad who worked with me, Jim Brin and Sequoia Beckman at Berkeley. We'd also like to thank the whole CloudMinds engineering team, Bill Huan, Robert Zhang, who are co-founders and CEOs of the company, and this entire engineering team who supported me in building this all these demos. And Happy Robotics, Holly Trusett from CMU, Matt and Dave and Curtis have helped me tremendously of putting that whole robot together and then integrated with their APIs, these CloudMinds APIs, in fact. And then I would also like to thank Bob Rada, CEO of the company, for a lot of recent evidence work. With that, open up to all the questions.
So in the initial part, you had experiments with gas.
Yeah.
So how likely the mission will fail if you use if your network has a packet loss?
It's very unlikely because the motion actually. So I was showing you the 2x speed up. So the entire motion is actually about 2 seconds. Mm-hmm. So when the package lost, and you just send another one in the latency. I mean, it's very likely that, it's gonna get there in time in order for the robot to make decisions to pick it up. So we don't actually execute that decision until it is in the middle of the motion.
Is that also saying for the learning phase?
So the learning phase is actually just, we are actually just loop through all the high probable grasping recommendations and then perform that one each, and then we collect the result automatically from the system. So that's the empirical kind of experiment part, but in the cloud, it's actually collecting all this data and then re-ranking all this grasps based on their success rate.
So during the learning phase, if you lost some data obtained when you learn, it means
Sure.
we are short for some data there, right?
That's a good question. So we didn't actually make a guarantee so that the data wouldn't lose, but in concept you can program it so that it guards like every single data performance can be accounted for. So this is the beauty of the cloud, like a centralized control system, right? Because you always on the high level, the execution were all sent it from the cloud, so you actually know what should be accounted for and what should not be accounted for. This is a little bit different from like a decentralized system where you may not in the system, every single agent has that kind of knowledge. I'm not saying, cloud is solved everything, but I'm saying in this scenario, it actually makes sense to keep track of everything.
Thank you.
Go ahead.
Thanks. In semaphore recognition, which information is getting sent to the cloud?
Oh, the entire video frame.
The whole video, yeah?
The whole video.
Thank you.
Yeah. So with some of like a more recent local kind of edge device that can start handling gesture recognitions, you would imagine the more compact representation sent it to the cloud should be trajectories and then maybe like joint positions and all that. But currently, it seems like the most efficient way to have the system working at the moment because I'm not really into the embedded space, but there are solutions out there that can perform general gesture recognitions on a cell phone device.
Thank you.
Yeah.
Like the entire work, there is no, like you're not changing anything on the network side itself, right? You're using existing networks.
I'm using existing networks except for the cloud mines like VPN system.
Mm-hmm.
So they actually have their own protocols to deal with. They actually own their own access point too. So they did do special things, preparatory special things on the access point.
So what kind of innovations were required on the network side in order to enable, say, like real-time high bandwidth transfer?
Oh, what kind of?
Like what kind of innovations they required for those access points in order to enable, say, like high bandwidth real-time?
Yeah, so I'm not sure if I can disclose that information, but the only thing I can really disclose is it actually guarantees privacy and guarantees delivery, and then have optimum routing capabilities in those situations.
Well, given that this is the networking seminar, what can you tell us about the networking aspects of this?
Yeah, so I tried my best to kind of impose like the problems in cloud robotics that needed work in the network. But I think the main problem is latency. How do you deal with latency, and how to actually accommodate? How do you potentially build like a protocol or some kind of abstract layer that can handle this kind of latency with perception and robot control and dynamics all in one piece. So if there's like one takeaway for this network seminar, I would say how to deal with latency, how to mitigate this latency on a large level, and then it's kind of like the point of what I'm trying to say. So hopefully like that's the biggest problem of this cloud and edge hybrid is this network. It can be as reliable as it can be, but then when the network is gone, what do you do? like a lot of the autonomous, for example, right? So if we are going, in this example, if I don't have the cloud and perception, this robot will still stand. It will not fall. So all the dynamic control is on the robot. But we are actually, so when I use the hybrid, I didn't intend to use it that way. I intended to say this is the cloud and the edge device hybrid. But they're in control, there's actually the hybrid system. This is a form of hybrid system where you provide discrete command from the cloud and then guarantee stability and then all the transitions in the control system itself. So, this actually guarantees, as long as there's power on that robot, this robot will stand. And then it would hold its postures and that, but then it would not change its configuration, or it would not move around or pick up object. Because all those, it requires information coming from the cloud, coming from high-level perception and path plannings and all that. So I don't know if that answers your question, but like.
Well, to focus things a bit, since apparently you can't tell us how they actually solve the problems of how they actually solve the networking problems in the system, can you at least tell us what you think, or if we as networking researchers could solve a problem for you, like what problem would that be, or like what are the things that you would like the network to do for you that it can't do today? Or like what are the problems, what are the problems that the network causes for you? And one of them, I guess you said, is latency.
Right.
And you solve that apparently, I think, in the standard way by moving your cloud closer to the robot.
Sure.
And having autonomous local processing. And then the other problem was connectivity, and if you lose connectivity, then you have local autonomy. But like, what could the network do to make things better for you?
So there's the things I want, right? Like, I think what I really want is a hybrid system that can perform online learning. So it would actually be able to learn what you have from the real environment, and then would be able to share with the cloud. And the cloud will learn with all these many agents in the field, and then give you a better policy. I think that's kind of like online learning, kind of machine learning scheme where you want to do online learning, kind of extension of the connected learning, will be built. The other thing I think is a synchronous kind of communication where you have to tie this with perception, right? So if I intended to do something, and then the perception system figure out what I intended to do, and then can actually predict what I intended to do, and then send it over to the local robot, and the robot's supposed to use this information to make a trajectory and in response to that intent. But as soon as that intent changes, then the system would also change. So that's asynchronous communication, but it's not kind of like timely asynchronous communication. So how do you actually combine this kind of, you don't know when the intent or this information gonna come out in the system, and how could the network can send it to the robot, and the robot system itself can actually respond to this unexpected intent all the time, like without having to send maybe 100 hertz of information. I want to send maybe only 10 intent in the last minute, and they are all sparsely, like they're all sparse informations, and they're all like pieces all together without the regular interval. How do you actually deal with this? How do you make a network policy like that? I think that's something I would like to see coming out. I don't know if it's already there in the network systems, but.
Yeah, I don't really understand what you're trying to say. You're saying what?
I'm trying to say, so the intent of the human, the inference coming from the cloud or for the intent of human can actually come in sporadically, unexpected, not in a regular interval, but the robot need to recognize this, can take this signal and then perform certain executions, but at the same time, it still need to be able to absorb the uncertainty that will come in for the next intent. How do you actually do that on a network layer? We can talk more.
No more questions?
Question is,
in this case, is there more information being pushed up into the cloud from the sensors and visual than is being pushed down? Because what's being pushed down is more like commands, it sounds like.
Yes, but I want to, so right now it's a preset commands, right? Like, pre-generated of some form, but I want to expand that so that it can generalize. In a sense, we are actually kind of solving this problem right now with the gesture data. We want to actually do general gesture following. So in a sense, we want to segment out meaningful gestures. Pre-process all this gesture, and we want to segment it out, and then we want to use our imitation learning system to be able to respond, either imitate or interact with the system. So it's kind of making a different assumption because if you have like a general gesture following system that the server is sitting right behind you, you wouldn't have this problem. But think about this: us as human, the command coming from the brain to your muscles or through the ganglia of your spines, those commands are not in regular intervals. Those are actually, that's why sometimes I miss, when I'm trying to catch a baseball, I miss it because, I actually have very high latency between my brain and my muscles, but yet we can actually perform all this very, sophisticated task. So what is the policy that mimics the neural connections within the brain, and then how do you actually, replicate that, I guess, in that perspective. So that's so I don't think the latency is going to be a problem. If we do this right, 200 milliseconds is a little bit worse than a typical human being. I think human being is probably something 100 milliseconds is like the bar of the HRI, right? So human being can handle up to 100 milliseconds, but how do we actually perform this? How did our spinal cord remembers all these motions on executing, send it from the high level command? That's kind of the system I either want to build or investigate how to handle the general service robot scenario. Yeah.
Do you worry about power consumption in any way?
No, I don't. Do you want to?
No, just wanted to ask.
The
power consumption.
No.
Okay.
Yeah. Oh, power consumption.
Yeah.
Which power consumption?
Of the robot.
Of the robot.
Yeah.
I don't know exactly. The phone can probably last for a couple of hours. I forgot how many watts it consumes.
Mm-hmm.
But if you actually perform you use this LTE and then send it up to the cloud, the phone can last, if it is alone, it can last 2 to 3 hours. And then if you attach it to a robot which has battery of its own, it can last as long as that robot lasts.
Mm-hmm.
But if you were to put a deep learning module on it, depends on the system. If you have a dedicated chip or not, some of the FPGA chips can actually handle half a watt nowadays to perform pretty good inferencing. Then it depends on when that technology would arrive, and even if that technology did arrive, how do we actually use it for large-scale robot deployment?
Actually, just add one robotics question. For your last robot, the self-balancing robot, did it have touch or pressure sensors? So
yes.
So it could tell when it was getting resistance from the box as it was picking it up.
Yes.
Or if you as a human were yanking it away, it could perhaps detect that as well.
Yes, it can. You can actually respond to that too. So that's a very good point because grasping itself have nothing to do with vision. Vision can give you cues.
Without feeling it.
Yeah, as long as you know where it is, you can actually pick it up. So Happy Robotics actually have all those very specialized modules where the forward and then backward kinematics helps you to infer the direction of force, pressure that go onto the end effector. So it's actually pretty good technology. But those are also very expensive technology. But there's potential things you may be able to do. For example, if you just have pressure sensors on the hand, you may also be able to do similar things. But you won't be able to use the directional information coming from those pressure sensors.
Yeah, I think that's what your hand does, is you flow pressure.
Yeah.
It's not running some complicated forward and backward kinematics, and as you mentioned, the latency of your brain or even your spine might be too long anyway.
Right.
So
right, but the issue is this: it's like large scale. If you us sensors, right? Like there's a million sensors just on this single spot.
True.
But most of the piezoelectric sensors, you can maybe do 20 by 20 or something. It gets very expensive. So there's a new technology from MIT, gel site, and that can potentially just look at how much pressure you can put from images. So that's a very good potential technology to use in this application, where you only need maybe a couple cameras, but you can infer the general pressure kind of distribution of this anti-effector, and then that would be very cool. I would like to see some work on that myself.
Well, great. I also noticed the mistake at the end where the robot dropped the cube, and I was like, oh, the robot, somebody made, or the operator, I think, didn't determine the correct point at which the human had fully grasped the cube, right? And
Yes.
was ready to take it, right? So that was an interesting disjunction at the end where this mistake had been made, right?
Yes. If there's any chance, maybe we can show you how this teleoperation system works. So it actually came with a joystick originally, but it only goes through the typical short-range communication, and we integrate it with LTE. but the short story is, even if
And
you're
by the
looking
way,
at
we
the
should be
screen-
wrapping this up soon, so if you want,
even if
take
you're looking
discussions
at
outside.
the screen, it's very unintuitive to control this robot. It would take me 30 minutes to pick up an object, whereas if I code this autonomously, it can do in 30 seconds.